Okay, so now what I want to discuss with you is the differences between a classical harmonic oscillator and the quantum harmonic oscillator. Okay, so versus quantum harmonic oscillator. So let's start with the classical harmonic oscillator. Now that's something that you already learned in previous classes. So what do we know about the classical harmonic oscillator? Its energy involves the kinetic energy and the potential energy, which is the potential energy for the harmonic oscillator. So it's 1/2 of m omega squared x squared. And here now we are playing with numbers, no operators, no, because this is the classical harmonic oscillator. Well, if we wanted to make plots, if I want to make a plot of the potential energy, so how are we going to do this? So this is X. We want to make a plot of the harmonic oscillator. I'll put this curve in blue. Well, this is the harmonic oscillator. X there is x squared. So what we have is a parabola. When x is 0, the potential is 0. As x becomes large, the potential energy becomes very large. So this is a parabola. All right, good. Now, how about the energy? Now, if I want to put the energy in this plot, well, the energy is constant, it doesn't change. So I'm going to put here the value of the energy. And how about now, if we want to make a plot for, if we want to put in this plot, the kinetic energy. Well, let's see. We know how to do that, but let's see what helps us. Let's assume that we have a spring with no friction, which behaves as a harmonic oscillator. So let me make this picture here. In its natural length, it's right here at this position 0. But if I give some energy and I stretch it, I'll stretch it up to this amplitude A, because the amplitude is determined by the energy for stretching it. So if I stretch, I put it here at this position A, which is the amplitude of this motion, and now this box or this part will start moving back and forth. Will be moving back and forth. Once it passes through this position 0, it will have the maximum velocity, right? Once it reaches the other extreme, this minus A, it will stop. So let's make a plot for it here. So once it becomes maximally now compressed and reaches this position minus A, it stops. And so what we have here is the velocity here is 0, the velocity here is 0, and right at x0, we get the maximum velocity, right? So if now I have to make this plot for the kinetic energy, I know very well, maximum is here, 0 at the extremes. So the plot for the kinetic energy is this one. So that's what we know from classical mechanics. So let's think a little bit. You see that right at this position here at x0, when the velocity is maximum, I have a very small chance of finding the particle there because it passes very quickly. So small chance to find our object, our classical object there. And where do we have a higher chance? Closer to the edges, no? When it's very close to the positive or the negative extremes here, because it's reaching this point very slowly. So at these extremes, there is a large chance, a large probability to find these particles. Okay, this particle. All right. And another important thing, we know for sure that we'll never find this particle around here, no? Or around there. It will never be there because it doesn't have energy to be there. For the energy that started this process, it will never be there. So this whole region here, beyond the amplitude, is classically, put it in black, no? Is classically prohibited or classically forbidden. And the same thing on this region here. This region here, we cannot find the particle there because it doesn't have energy to be there. Classically forbidden. Okay, so this is very important. This is what we know classically. Now let's try to compare what we discuss here with the quantum harmonic oscillator, and you will see how things now change. So let's talk about the quantum harmonic oscillator. And for the quantum harmonic oscillator, quantum, we know that all information is contained in the wave function, in the solution of Schrödinger's equation. So let's write Schrödinger's equation. Now, just to simplify the notation, I'm going to introduce a variable c here, just so I don't need to keep writing this m, omega, h bar. So it's playing the role of my position, but I introduced this variable just so I don't need to keep writing the square root of m, omega, and h bar, okay? And what is the solution for the harmonic oscillator? The solution is, this was the normalization factor for the ground state, okay? But for the first excited, second excited, we have more terms which are contained in this square root. And also in this function of Hn, I'll tell you in a minute what it is. And here the exponential of minus c squared over 2. So you see that this term here, if I write in terms of x, is what we are familiar with. Now it's exponential minus m omega x squared over 2 h bar. And what is this? This one receives a name. They are called Hermite. They are called Hermite polynomials. And it's just a simplified way to write in one equation all of the solutions of the harmonic oscillator. Because that equation for the Hermite polynomial, for the ground state, it is just one. You see, so then we recover what we already knew, the solution for the harmonic oscillator ground state is that normalizing factor. This thing here is just one. The Hermite polynomial is just one. And then we have the exponential. Well, if you go for the first excited state, what we get here is 2 psi. So it's 2, and that is square root of m omega h bar and x. So the equation for psi 1 has some constants, but the important thing is we have x here and the exponential minus m omega x squared over 2h. Well, let's go just one more. For the second, the second excited state becomes a little more complicated. You see that now we have 4 psi squared minus 2. That's why these things are called polynomials, no? Hermite polynomials. So then our psi 2 involves x squared, some constant, no? And then the exponential. Anyway, it goes on like this. If you want, you can see these Hermite polynomials in your book. It's contained in the table 2.1. But what are we going to do with this? We repeat that all information about a system in quantum mechanics is contained in its wave function. So let's try to make plots for the wave functions, okay? So here I'm going to have a drawing for our harmonic oscillator, so for the potential energy. And on top of this potential, we are going to try to draw the wave function. So here we are going to write the wave function. So I'm going to start with the ground state, and I'm going to make a plot, a drawing for that wave function. Well, it's a Gaussian, right? That's we know it's a Gaussian. So where is this function? Maximum, right at x0. So right here it's maximum, and then it decays. Well, we know that probability is the square. This is not so good. Is the square. So let me put our energy of the ground state. And now I'm going to show in this plot the psi n square, starting with the ground state. So the square of the Gaussian is similar to the Gaussian, a little bit more like a little narrow, but it's still the same behavior, maximum at x0, which is telling us that if the particle is in the ground state, the maximum probability to find it is at x0. This is just the opposite from what we said when we are dealing with the classical case. We said that at this position, so at x0, where the velocity is so large, we have the smallest chance to find the particle. Well, in quantum mechanics, if we are in the ground state, at x0, we have the highest probability. See? Completely different. And there is one more very interesting thing. Look at this. Let me put this in red. We have, or yellow, I don't know. We have here tails. No? So this point here is minus A classically, no? And plus A classically. But you see that quantum mechanics, there is a tail going beyond. There is a probability to find the particle outside, not beyond the, so there is a probability to find the particle beyond this extremes, this amplitude for the classical harmonic oscillator. So there is a probability to find the particle in the classically forbidden region. And we'll never find this particle there classically. But quantum in quantum mechanics, we can find it. So we say that when the particle goes beyond this classically allowed region, we say that the particle tunnels. It's tunneling. Okay, is this process that is a pure quantum mechanical process. Okay, let's continue with some more plots. As we go higher and higher in energy, now we saw that then we get x, then we get x squared, and as we go higher and higher in energy, you're going to see that we are going to get more oscillations. Let me make one more plot. For the first excited state, the plot is something like this. Okay. And if I make this plot for the probability, we'll see that now we have these two oscillations. Okay? And if you go higher and higher, you will see more and more oscillations showing up. So let me make one more for the energy E2. So the second excited state, you're going to see that we have something, always this tail, no? In the forbidden region, no? And then here and there. And if we make now this square, we have this, and this. My drawing is very bad. I suggest that you look at the figure 2.7 in your book to get nicer figures. But the important thing is we are getting now, as we go high in energy, we are getting more and more oscillations. Eventually, if you go to a very large energy, for example, 60, and you try to draw that probability, the probability density, you will see something very interesting. Let's see if I can give you an idea, but again, look at it in your book to get a nice figure. We are going to get something that many oscillations, and it starts big at the edges and it goes on something like this. My drawing is not so good, as I said, but we are now approximating that potential energy that we have classically. Okay, so now when we go very high in energy, we see that now the probability to be here in the middle, now it's becoming small, and at the edges, it's becoming large, similar to what we have classically. But we have to go very high in energy. So fascinating, these differences between the quantum and the classic. So what we did here was plotting the potential energy for a very, the probability density for a state with very high energy. So coming back to that ground state. So the ground state is the most quantum scenario. So this was our potential. Let's call this the energy of the ground state. And if we make that plot for the probability density of the ground state, we had something like this with a tail. So what this is telling us, there is a chance to find the particle beyond the classically allowed region. The highest probability is right at the center at position 0. So just the opposite of what we have in classical mechanics. And then there is a very interesting problem for you to solve, is the problem 2.14, which is exactly that. So if we can find the particle outside the classically allowed region, what is this probability? Okay, so this problem 2.14 is, what is the probability of finding the particle outside the classically allowed region. So in the classically forbidden region. How would we compute this probability? Well, what is the classically forbidden region? Is the region here, no? Before minus a, so from minus infinity to that minus a, and we are thinking here about the ground state. So this is forbidden region, and forbidden region is also here, beyond this amplitude plus a. So to get this probability, you need to compute this. Yes, and what is this A? What is this amplitude? Well, this amplitude comes from the classical motion. So from the classical motion, what do we know? That the energy is p squared over 2m plus 1/2 m omega squared x squared. How do we find the amplitude of this motion? Well, right once the particle reaches that maximum displacement, the amplitude, that's when the velocity is zero. That's when the particle stops. So at that point, the momentum becomes zero. So here we have that the energy is half m omega squared a squared. So this zero is in this scenario when we reach the maximum displacement is in the positive or in the negative side. And from here, we get what this A then is. 2 energy divided by m omega squared and the square root. So this is what you have to put here and there. And then you have to solve this integral. And that's the end of this discussion.